Okay. Sorry for the pause. So during training, we train the group VIT jointly with the text encoder. We are on the noisy image text pairs, just like clip, and the grouping automatically emerge without using any mask annotation. And during inference, we could zero transfer these groups to semantic segmentation without any fine tuning. We just extract the group first and then assign the label to each group by given the test category of the testing data set. Here we show the details of group VIT architecture and show how we group the image into different parts. Given an input image, we first project the image, split the image with into patches, and then project them with a linear layer. Besides this projection gets the gets the image tokens, we also randomly initialize a set of group tokens, which are learnable. And we concatenate these tokens together, feed them into the transform block and the grouping block. In the grouping block, we will calculate the similarity between the group tokens and the image tokens, and assign the image tokens to the groups. Here's the visualization of the grouping assignment. Each group token actually represents one region in the image, and this region is image conditional and learnable. This is actually the stage 1 grouping. After the stage 1 grouping, we could further grouping on top of this stage 1 grouping result to merge the small regions into larger ones. In this process, we are actually merging the irregular shaped groups and the irregular shaped visual concept in a hierarchical way. And this is the second stage grouping. After the second stage grouping, we will contrast it with the global feature of the output by the network with the text embedding of the image pair, of the text pair. Here is some additional visualization. This will help us step deeper into what have been learned by the group token. We visualize the attention area of each group across the different image on the data set. And interestingly, we found that some tokens will focus on some specific concept that match our mindset. Here, in this token, it's a block. It's a group token 5, and it's always attend on the human eyes or animal eyes if there's eyes in the image. And this another token will focusing on the limb of the animal or human if there's a hand or the feet of the animal. It's very interesting that if the human is present image, human has hand, and this token will focus on the hand. But if the animal is present image, most animal does not have the hand like human. This token will focus on the feet like the bird and the dog. This is the stage 1 group tokens. And in the stage 2 group tokens, these tokens are more likely to focus on some high-level concepts, such as the body of the human and the face of the human. And here we show some quality results on different test data sets, such as the Pascal VOC, Pascal context, and the COCO data set. Our model could generate some reasonable groupings regardless of the data set we are using. And this model does not require fine tuning all the training set of the data sets. To summarize, firstly, the group VIT explores self-attention in the transformer layers and the hierarchical grouping the visual concept into irregular shapes. And this is also the first work that tries to learn from text supervision and transfer the grouping to the semantic segmentation without using any mask annotation. And lastly, we've also found that this grouping has a potential to generalize very well to different testing data sets of different categories without any fine tuning. And our code is also publicly available. The main poster session will be in Friday 4.1. Please visit that at post session at that time. Thank you very much.
Hi everyone. Good morning. I'm Hakan Biran. So the first slaughter couldn't make a way home because of visa issues. So today I will talk about cross-domain few-shot learning with test-specific adapters. Okay. So in few-shot learning, our aim is to learn a classifier from few images only for previously unseen tasks. a set of categories. And here you can see that, for example, this is done in a way that we get a support set during meta testing period. So we have 3 categories with 3 images each, and given a query image, we would like to classify it to the one of the correct to the correct category. And so previous work, broadly speaking, split the learning process into 2 stages. In the first one, meta training, because we do not have many images in this stage, we go to a big data set and then pre-train a classifier, feature extractor. And in the meta test stage, we adapt the classifier to the this task with FIV images. And typically, we learn just a classifier. We freeze the rest of the network and learn a classifier on that. So recently, the focus of the community has shifted to a more challenging setting where during meta training stage, we get some domains and then we learn a feature extractor from them. But in testing time, we are getting support images from previously unseen domains. So this is very challenging because we have, for 2 reasons, we have a large generalization gap. So here you can see, for example, these are the train categories and these are the meta test categories. They look completely different. Another problem here is, another challenge is that we have very few images to close the domain gap. So at the meta test time, we have very few images to learn and close this gap, domain gap. So the existing solutions, again, in meta training set stage, go to a large training set from which consists of multiple domains. You train a classifier on them. So this is a task agnostic model. And this time, instead of just learning the classifier, we only learn task-specific adapters, because this is a more data-efficient way of doing it, because you cannot train the whole network on FIV images. So our contribution is we systematically study this task-specific adapters. So previously, there were many works with different design decisions. So here we do a systematic study of how they should be estimated, this task-specific adapters, how they should be connected to a network, and how they should be parameterized. And in addition, we also show that the optimal setting outperforms the state of the art, especially when there is a big domain gap between train images and test images. Okay, so let's start with an overview of what is task adaptation. So typically, we have a, let's say, a RESTnet with multiple modules and blocks. And so we have a support set, and then in the we use a nearest mean classifier, so which takes the features, takes the images, extract features, and then take their mean per category, and then find the assign the query image to the closest mean to that category. So as I mentioned, so the training the whole network on FIV images is like too expensive, and then it will overfit. So the recent papers add some compact adapters, which is indicated with R alpha with these green blocks. So we just freeze the network and learn them. So the first question we ask in the paper is, how should we estimate them? So these adapters. So one way of doing that one is having a meta network, like hyper network kind of network. It's shown with n lambda here. So it basically takes the n lambda and then outputs the weights of the adapter, basically. So it's estimation done through a network. And we also look at other strategy, which is like maybe more straightforward. So we just add adapters and then learn them on the small support set in the second, on the right image. And we also study how they should be connected to the network. For example, you can connect them in a serial way. So given, for example, a 3x3 block in ResNet, we can just add them in serial way. So then it's like composition of two feature maps, two operations, convolution and the adapter. And also we also connect them in a residual way. So this is inspired from residual networks. The advantage of this one is obviously you do not make the network deeper. You make it just parallel, and then gradient flows in a better way. And finally, we also look at how they should be parameterized, the adapters. So one way of parameterizing them, just as simply doing a channel-wise scaling operation, and this is more compact and efficient. We can also have a matrix multiplication. So this is given a feature, given a coordinate in a feature map. Okay, so in short, what we found best working optimization, best working configuration was directly attaching the adapters instead of estimating them through another network, connecting them in a parallel way, and then using matrix form parameterization. And then we evaluated our method in the augmented metadata set, so which has 8 data sets for train, val, and test, and then in the for test only we have unseen 5 data sets, and we use our previous model for the backbone URL backbone, and we evaluate average classification accuracy for various few shot tasks. So here you can see the seen domains and unseen domains in this data set. So in our analysis, first we look at how they should be estimated, and then we found that learning them directly from the data, optimizing them on the data is much more effective. So it's quite noisy to estimate them through a network, directly splitting the parameters of the adapter. Second analysis we had is they should be connected serial or parallel, and then we found that parallel connection is more effective. Finally, we look at channel-wise and like to their parameterization, and then we found that matrix form is better, though channel-wise has less parameters. So this also offers a good trade-off. Okay, so after we found the best configuration that I shown you in the previous slide, we compared to previous work, state of the art. So here I'm showing the average over all the categories. So we obtained the best results, significantly better results than the previous work. Okay, so this concludes my talk. You can find the code and more material in the link here. Thank you.